Wunsch-Bell characterization is also a topic that I was working a lot on that. Have you ever heard Wunsch-Bell characteristics? Okay, then just some. So it was in the beginning of the microelectronics industry, especially in the US during the Cold War. They were very afraid of a nuclear attack from Russia or wherever. And quite a lot of scientists were working on the topic, how can we improve the robustness of our ICs against electrostatic discharges. So not just electrostatic discharges when a human person is touching something, but also nuclear NAMP pulses, for example, nuclear electromagnetic pulses. And there were two scientists, Mr. Wunsch and Mr. Bell, and they found a very nice characterization technique to characterize how robust is, in this case, a p-n junction. So a diode, as I mentioned before, as used as an ESD protection. And the way how they did it, they were using transient pulses, in this case, rectangular pulses, and they were injecting these rectangular pulses into ESD protection structures, like diodes. And they were measuring the voltage and the current, or the voltage across the diode and the current that goes into the diode. And this is all based on a so-called TLP system, a transmission line pulsing system. And this is a system that is generating very sharp rectangular pulses. The way how the system is working can be then further introduced in the lab. So we have several TLP systems, but the basic idea is that we are charging up a coaxial cable as a kind of charge capacitor, and then we are discharging this coaxial cable, and depending on the length of the cable, we are generating a reflection. And there is a reflected pulse going in this direction, the other one goes there, and the sum of all the pulses, the sum of these two waves are then ending up in a rectangular pulse. And the length of the pulse is defined by the length of the coaxial cable. And the amplitude of the pulse is defined on how much voltage we are putting on the cable. So we can easily control the amplitude of the pulse and also the length of the pulse, and this is what these guys did. They were using different amplitudes and different lengths of the pulses and inject these pulses into a device on a desk and measuring the voltage and the current. While they were characterizing that, they were increasing the amplitude until this device was breaking. And very often the devices, in this case, were breaking due to thermal destructions. So what they did, or what we are then finally doing in our lab, was we are measuring the voltage and the current. So for example, here on the x-axis, you can see the voltage of the pulse, and on the y-axis, you can see the amplitude of the current. And we are beginning to inject some voltage pulses at a certain pulse duration, in this case of 100 nanoseconds. And we were increasing the amplitude of this pulse with 100 nanoseconds, increasing the amplitude, measuring voltage and current, increasing again. And for each amplitude, we get 1 point here in this IV characteristic. And then you can see there is a breakdown voltage. And here at this point, when the voltage exceeds 28 volt, for example, the current begins to flow. So our diode is now conducting. And then we were increasing the amplitude until here we can see something happening, and this was then the point where the diode was finally destroyed. And the last voltage and current value, so this voltage value here and the last current value here, was then transferred as a power information into a diagram. So here on the diagram, we have on the x-axis the pulse duration, so this 100 nanoseconds, for example, and on the y-axis, we have the power to failure. So the power that was really injected into the device short before it breaks. Okay. So again, on the x-axis, we have the pulse duration, and on the y-axis, the power that causes then the failure. So we were increasing the amplitude until we have a failure, and then you get 1 mark in this diagram. And if you're then doing this for different pulse widths, so for example, 100 nanoseconds, 200 nanoseconds, and so on, and also for shorter pulses, you get this so-called Wunsch-Bell characteristic, which gives you some information how robust is your IC, in this case, your input structure, your diode, when it's about any kind of transient disturbances. And the cool thing that can be done is we can also include other pulses into this diagram. So this is what we did with the so-called automotive pulses. They are not super rectangular, so they are exponentially shaped in the rise time and exponentially shaped in the fall time, but we can make an equivalent rectangular pulse out of this, whatever it's shaped pulse, and we can then take a look in this Wunsch-Bell characteristic if this automotive pulse is then below this area here. Below means everything is safe. The ESD protection structure or the diode that is used in the IC is able to handle this amount of power. But if the pulses like this load down pulse or test pulse 1 or test pulse 2A are then above the limit, we definitely know that this IC will never ever survive thermally this transient disturbance. In this case, we could then finally characterize how robust are these ICs against any kind of transient disturbances.